Hey everyone, and welcome. Today we're going to deconstruct a really classic physics experiment. The goal? To get to the bottom of one of the most fundamental laws of motion out there. We're going to see, step by step, how scientists figured out the link between force and acceleration. So, let's just dive right in. Everything we're looking at today really boils down to this one simple question. How are force and acceleration actually connected? I mean, you know this intuitively, right? You push something, it starts moving faster. But what's the exact relationship? Is it a simple one-to-one thing? That's what this whole experiment is designed to figure out.
All right, so here's our game plan. We're going to walk through the entire scientific process. You know, the whole shebang. We'll start with the experimental setup, then look at gathering the data, graphing the results, figuring out what it all means, and then, the fun part, putting that law to work.
Okay, first things first, the experimental setup. And let me tell you, getting this part right is absolutely crucial. Seriously, one tiny mistake here can throw off all your results later on. So let's take a close look at the gear they're using. Okay, so here's what we're working with. You can see the trolley sitting on a runway, and it's hooked up by a string to this mass holder. The whole idea is pretty simple. The weight of those masses is going to pull the trolley. And that gadget you see, the light gate, is connected to a data logger to get a super precise measurement of the trolley's acceleration. And this is a big but. There are a couple of problems with this setup right out of the gate. So problem number one, the trolley is actually rolling down the runway all by itself even before we've added any pull from the masses. Now, you might be thinking, why is that a big deal? Well, it's a huge deal because we only want the force from the hanging masses to be what's causing the acceleration. Any extra little push from gravity just because the runway's on a slope, that's going to contaminate our results. The fix, luckily, is pretty simple. You just adjust that wooden block until the runway is perfectly horizontal. And then there's problem number two, friction, the enemy of so many physics experiments. See how the string is just rubbing against the edge of the bench? That's creating a drag force. It's working against the pull of the masses, and it's slowing the trolley down. That means we're going to get inaccurate readings. The whole goal here is to minimize friction as much as possible. And the classic, simplest fix for this is just to pop a pulley on the edge of the bench. That way the string can run over it nice and smoothly. All right, so with our setup now corrected and ready for a fair test, we can finally move on to the next stage, actually gathering the data. So let's take a look at what the student recorded. And here we have it, the raw results. That first column, resultant force, that's just the total force making the trolley move. In this experiment, that's the weight of the masses hanging off the end. So what the student did was gradually increase that force and then measure the trolley's acceleration each time. And you can probably already spot the pattern, can't you? As the force in the first column goes up, the acceleration in the second column goes up too. Okay, a table of numbers is great and all, but if you really want to see the relationship between two variables, nothing, and I mean nothing, beats a good graph. It's like turning that list of numbers into a picture, and a picture, as they say, can tell a really powerful story. So, if we're going to build a proper scientific graph from this data, there are three key steps we've got to follow. First, you need to pick a good scale for that horizontal x-axis, one that spreads your data out nicely so it's easy to read. Second, you have to carefully plot each and every data point from the table. And finally, step three, you draw a line of best fit to show the overall trend. So here's our blank canvas, so to speak. You can see the vertical y-axis is already labeled and scaled for acceleration. So our job is to get that horizontal x-axis scaled for the resultant force, plot those 5 points we saw on the table, and then draw that super important line of best fit. Okay, so fast forward a bit. Imagine we've plotted all the points and we've drawn our line. Now comes the big question. What does it all mean? What is this graph actually telling us? This, right here, is that aha moment of discovery in any experiment, when you finally interpret the results. And the conclusion is just beautiful. What you'd see is a straight line that goes right through the origin, the 0, 0 point on the graph. And that very specific shape, a straight line through the origin, tells us something huge. Acceleration is directly proportional to the resultant force. Now, what does that actually mean in plain English? It's simple. If you double the force, you double the acceleration. If you triple the force, you get triple the acceleration. They go up together, perfectly in sync. And this discovery, this direct relationship, it's not just some neat little pattern we found in a lab. No, this is one of the absolute cornerstones of classical physics. It's a fundamental law that governs how everything moves, from this little trolley all the way up to planets orbiting the sun. You've probably heard of it. It's Newton's second law of motion. And it all gets summed up in this incredibly simple yet unbelievably powerful equation, F equals m times a. Force equals mass times acceleration. This is what our entire experiment was built to prove. You could call it the official rulebook for how things move.
All right, so now we've got the law, we've got the equation. Let's actually put it to work. This is where the magic happens, right? This is how physicists use these fundamental principles to predict how things will move. So let's walk through a calculation together. Okay, so the problem wants us to find the acceleration of a 0.60 kilogram trolley when a force of 0.375 newtons is pulling it. First step, always, is to state your formula. F equals m times a. But we're looking for acceleration, a, so we need to rearrange it. A little bit of algebra gives us a equals f divided by m. Easy enough. Now we just plug in the numbers. So that's a equals 0.375 divided by 0.60. You pop that into a calculator, and you get 0.625. But wait, we're not done. The question asks for the answer to two significant figures, which is just a way of keeping our answer's precision consistent with the numbers we started with. So we need to round our result. And there you have it. Our final, correctly rounded answer is 0.63 meters per second squared. Pretty cool, right? Just think about that journey. We went from a hands-on experiment to a visual graph to a fundamental law and then finally to a calculation that can predict the future in a way. That, right there, is the power of physics. But you know, a really important thing to remember in science is that no experiment is ever perfect. There are always ways to make it better. To improve this one, for example, and reduce the impact of random errors, you'd want to repeat each reading a bunch of times and then calculate the average. That helps smooth out any weird fluke results. Or you could use more precise equipment, like an electronic balance to weigh the masses. Even improving your technique, like making sure that little card on the trolley doesn't wobble as it goes through the light gate, would make your results that much more reliable. And that really brings us to a cool core idea in science. There is always more to investigate. You know, we worked hard to account for friction from the bench and the slope of the runway, but what about other forces? What about air resistance? I mean, it's small, but it's there. What about the mass of the string itself? It's not zero. See, every answer you find in physics just opens the door to a new, more interesting, more precise question. Thanks for coming along for this breakdown.